Let's now learn about displacement and vector subtraction. Okay. To do this, we'll consider a couple of examples. Imagine I'm taking my dog for a walk at the park, and I'm trying to get the dog to come to me. And initially, this dog is standing 10 meters to the east of me, Mr. Schmidt. So here's the dog's initial position, and I'll represent that with this vector x1. Then I ask the dog to come to me, but the dog runs past me and comes to a stop 6 meters west of me now. Here's the dog's second position, and let's mark that x2. Now let's represent the dog's displacement, that is, the dog's change in position. It extends from the head of x1 to the head of x2. I could draw it like this, but it's really hard to see when I draw the vector like this. So instead of drawing it on top of the vectors, I'm going to draw it just above. Okay. When we represent vector sums and differences, as this is, in one dimension, we'll draw a parallel. We'll make the vectors parallel to each other instead of right on top of one another, so it's easier to see. But there you have it. I've represented the displacement, the change in position, and note that it extends from the head of vector x1, the initial position, to the head of x2. This is the, right here, this is the initial position, and right here, this is the final position. Okay. What was the dog's displacement? Specify magnitude and direction. Well, you could see on the diagram here that the dog has displaced from 10 meters east all the way to 6 meters west, and that is a displacement of 16 meters west. Okay. Okay. Since we are working in one dimension, though, we can just use addition and subtraction to find this answer. Let's write this like this: delta x equals the final position minus the initial position. Here's a general formula for displacement. Okay, and so I have 6 meters west minus 10 meters east. Now, I can't add and subtract west from east. Both of these have to either be indicated along the east axis or the west axis. So I'm going to change 10 meters east to west, like this. 6 meters west minus negative 10 meters west. Okay. And now I think you could see that we end up with this answer, 16 meters west. Next example here. Okay, 20 minutes later, Mr. Schmidt watches the dog undergo a displacement of 9 meters south as it runs past him. So here we have the displacement. Here we have the displacement, and the dog comes to a final position or a stop at 4 meters south. So that is the final position. Okay, so I'm going to start by representing the dog's final position. Okay, the dog's final position, 4 meters south. Let's represent that on the diagram with this position vector, x final. And now let's draw the displacement vector. So we know the dog travels 9 meters south, so we need a vector which points 9 meters south and ends up at the 4 meters south location. So we've got, here's 4, 6, 8, 9 meters. So this is our change in position. And now we can draw on this diagram a vector to represent the dog's initial position. This is x initial here. And you could see that it's 5 meters north from the diagram. Let's calculate it with the formula. So we have delta x equals x final minus x initial. We can rearrange this by adding x initial to both sides and subtracting, and so we'll get delta x plus x initial vector equals x final, and then we can subtract delta x from both sides, and we get x initial equals x final minus delta x. And now we can put the numbers in there. We have 9 meters south. Sorry, that's delta x. We have x final is 4 meters south minus 9 meters south, the displacement, and that gives us negative 5 meters south or positive 5 meters north.